Welcome to The Explainer. Today we're tackling a really big one of the most mind-bending ideas in all of science, actually. We're talking about Albert Einstein's special theory of relativity.
So let me ask you something that sounds, well, kind of simple. Is time the same for everyone? Your first thought is probably, yeah, of course it is. A second is a second, right? Doesn't matter if you're here or on the other side of the planet. But what if I told you the universe is a whole lot weirder than that? And that your common sense is, well, wrong?
Okay, so here's how most of us think about the world. On one hand, you've got this idea that space is just there. It's like a rigid container. And time, that's this universal clock, just ticking away. The same for you, me, everyone. But then Einstein comes along in 1905 and just flips the whole thing on its head. He says, nope, space and time aren't separate things at all. They're woven together into this one dynamic fabric he called space-time. And the crazy part, this fabric can actually stretch and warp based on how you're moving.
So how on earth do we even begin to wrap our heads around this idea of a flexible reality? Well, to get there, we have to go back in time a bit, to a huge problem that was bugging physicists. See, by the end of the 1800s, two sets of fundamental laws, the ones for motion and the ones for light and magnetism, were basically at war with each other. They flat out contradicted each other. And you can't have that. Something had to break.
And this is where Einstein's genius really shines. Instead of trying to just, put a bandage on the old theories and hope for the best, he did something radical. He decided to just throw them out and start over. He thought, okay, what if I can find one or two super simple, absolutely unbreakable rules about the universe? His whole plan was to build a brand new physics from the ground up, based on those fundamental truths.
And guess what? He found them. It all boiled down to just two incredibly simple, almost beautiful ideas. But these two postulates, as he called them, were enough to completely revolutionize everything we thought we knew about space and time.
Okay, rule number one, the laws of physics don't change just because you're moving at a constant speed. Think about it. If you're on a super smooth train, you can toss a ball in the air and it behaves exactly like it would if you were standing still on the platform. Makes sense, right? Now, rule number two. This is the one that's a real mind-bender. The speed of light in a vacuum is always the same, for everybody. It doesn't matter if you're rushing towards a light source or running away from it. It's always measured at the exact same speed. That should not be possible, according to our intuition.
Now there's a little bit of physicist jargon here called an inertial frame of reference. Don't let the fancy words scare you. It's just a way of saying your point of view isn't accelerating. So you're not speeding up, you're not slowing down, you're not turning. As long as you're in one of those smooth moving frames, whether you're standing still or flying along at a constant speed, these two rules apply. The laws of physics and the speed of light are the two things you can always count on.
All right, you with me? We have our two unbreakable rules. Now, hold on tight, because if you truly accept that those two things are always true, the fallout is just insane. The world that emerges from them is nothing like the one you think you live in.
So what's the first casualty of these new rules? The idea of now. The concept that two things can happen at the exact same time for everyone. Get this. Imagine you're standing right in the middle of a train platform and you see two lightning bolts hit the track at the exact same instant. One way to your left, one way to your right. For you, they were simultaneous. But what about your friend who's whizzing by on a super fast train? From her perspective, she's moving towards the light from one strike and away from the other. So the light from one of them will reach her eyes first. For her, they absolutely did not happen at the same time. Who's right? You both are. Now depends on who's looking.
And that's just the beginning. This rabbit hole goes way deeper. It leads us to one of the most famous and bizarre consequences: time dilation. And let's be super clear here. This isn't some trick of the light or an illusion. Clocks that are moving actually tick slower than clocks that are standing still. The faster you zip through space, the slower you travel through time. And we know this is true. We've tested it with atomic clocks on airplanes and satellites. It's real.
How can that possibly be? Well, there's a brilliant little thought experiment that makes it click. Imagine a clock that works by bouncing a pulse of light between two mirrors. Tick, tock. Now, if you're holding that clock, the light just goes straight up and down. Easy. But what if I'm standing still, watching you and your clock fly past me at a huge speed? From my point of view, the light pulse isn't going straight up and down anymore. It's traveling a longer diagonal path. But remember rule number two, the speed of light has to be the same for both of us. So if the light is traveling a longer distance for me, but at the same speed, what has to give? The only thing left is time itself. Time must be passing more slowly for your moving clock to make the math work. It's the only possible answer. And it gets even weirder. It's not just time that gets all stretchy and weird. Space does it too. This effect is called length contraction. To someone watching from the sidelines, an object moving super fast will actually look shorter, squished in the direction it's moving. And from your perspective on that spaceship, you'd feel perfectly normal, but you'd see the entire universe outside your window as being flattened in your direction of travel.
Okay, so this all leads to a really famous brain teaser called the twin paradox. It goes like this. Imagine we have two identical twins. One stays on Earth and the other hops on a rocket and travels to a distant star at nearly the speed of light and then comes back. Now, from the Earth twin's perspective, the traveling twin's clock was running slow, so she should be younger. But wait a minute. From the traveling twin's perspective, it was the Earth that was moving away and coming back, so the Earth twin's clock should be running slow. So who's actually younger when they reunite? It sounds like a total paradox, right?
Well, it turns out there's no paradox at all. There's a crucial difference between the two twins' journeys. The twin on Earth, she was in a single inertial frame the whole time, just coasting along. But the traveling twin, she had to fire her rockets to get going, right? She had to slam on the brakes, turn around, and then fire the rockets again to come home. That acceleration, the speeding up and slowing down, breaks the symmetry. It means her experience was fundamentally different, and the result is absolutely clear. The twin who traveled is for sure younger when she gets back.
All right, so we've bent space, we've slowed down time. Where does all this lead? Well, it leads directly to the single most famous equation in the history of science.
You know the one, E equals mc squared. But what does it actually mean? Well, once you start messing with the definitions of space and time, you find you also have to rethink things like energy and momentum. And what Einstein discovered was truly profound. Mass and energy are not separate things. They're just different forms of the same stuff. Mass is basically super concentrated energy, and energy, in turn, has mass. You can convert one into the other.
And that c squared part of the equation? That's the speed of light, squared. That is a gigantic number. What it means is that you can get an absolutely mind-boggling amount of energy out of a tiny speck of matter. I mean, look at that number on the screen. That's the power locked inside a single gram. It's the reason nuclear reactors can power cities, and, well, it's also the terrifying principle behind nuclear weapons.
Okay, so this has all been pretty wild, right? Stretching space, slowing time, mass turning into energy. It's easy to think, okay, that's cool, but what does it have to do with me? Is this just some weird thing physicists worry about?
The answer is, it's everywhere. Special relativity isn't just a theory. It's a fundamental part of how the universe works and how our technology works. Giant particle accelerators, they literally wouldn't function if the engineers ignored relativity, because those tiny particles get heavier and experience time slowing down. Even the fact that certain particles from space, called muons, can reach the ground before they decay is direct real-world proof of time dilation. It even helps us understand that electricity and magnetism are really just two sides of the same coin. It's built into the fabric of reality.
So, in the end, I think special relativity offers us a huge lesson. It tells us that we can't always trust our gut feelings about how the world works. Our common sense is just tuned for our slow-moving, everyday lives. But the universe is so much bigger, so much stranger, and so much more wonderful than that. It really forces you to step back and ask a pretty humbling question, doesn't it? If we were so wrong about something as basic as time, what else might we be completely wrong about?